Okay, so in this one, I want to talk about a really incredible result called the fundamental theorem of algebra. If it sounds important, that's because it is. And this is something which is true about the complex numbers. It's a real benefit that you get out of passing from the real numbers and into the complex numbers. It turns out that when you pass to the complex numbers, um, polynomial equations always have solutions. Always. Other than very degenerate situations like 5 equals 4, which is not a polynomial, which is a polynomial equation, but of course has no solutions. But other than degenerate situations like that, polynomial the complex numbers give you solutions to polynomial equations. And in particular, if you have a polynomial expression over the complex numbers, then you can always find complex roots for that polynomial expression. And you're going to find that as you progress in your studies and you learn more and more math, finding roots of polynomials is going to be something that you are going to find a lot of benefit in doing. Okay, so let's talk about it. The fundamental theorem of algebra. See, the tension is one that you've seen a lot in your life. You know that for even simple polynomials like this one, x squared plus 1, this has no roots over the real numbers. When you exclude complex numbers from your view and you only are focused on the real numbers, there is no real number which you can shove into x squared plus 1 and get 0 out. But that's not the case when you're dealing with complex numbers, because we know that x equal to plus or minus I, these are solutions to this polynomial equation. Take the square of plus or minus I, you're going to get negative 1. Add 1 to negative 1, you get 0. So this polynomial all of a sudden has roots when you expand your view into the complex plane. What the fundamental theorem of algebra confirms is that any complex polynomial will always have a full flight of complex roots. A complex polynomial and all I mean by this is that it's a polynomial expression where the coefficients are allowed to be complex numbers and the input to it is also allowed to be a complex number. A complex polynomial of degree n, and to prevent that 5 equal to 4 situation, a complex polynomial of degree n greater than or equal to 1, okay, has n complex roots counted with multiplicity. Okay. This is the statement of the fundamental theorem of algebra that I want to go with. There are other equivalent statements, but we'll go with this one. Okay. Now, what on earth do I mean by counted with multiplicity? Let me just sort of illustrate this with some examples here. Let's take the complex polynomial p of z equal to z minus 1 times z plus 3i. Okay. Then this complex polynomial has roots. The roots are 1 and negative 3i. This is a degree 2 polynomial. Because if you expand it all out, you're going to see that you end up with a degree 2 polynomial. And these are its roots, 1 and negative 3i. And each has a multiplicity of 1. Each has a multiplicity of 1. Maybe I'll just, yeah. Each root has multiplicity 1. A so-called algebraic multiplicity of 1. Okay? Let's contrast that with the following polynomial. Q of z equals, I don't know, z minus 3 minus 4i squared. So this is also a degree 2 polynomial, because if you expand it out, it's going to involve a z squared in there. This is also degree 2. But now the roots, it feels like maybe there's only one, given by negative 3 plus 4i. If you plug that in to this expression, then, oh, no, I messed up. It should be negative 3. What am I doing? I'm sorry. I'm losing my mind is what I'm doing. It's 3 minus 4i. That's the root. And this root has multiplicity 2. This root has multiplicity 2. And that corresponds to the fact that we've got this square here. That square in the factorization of q of z is what tells us that this root here has multiplicity 2. It's kind of like it's a double root, a repeated root, okay? If you allow yourself to count multiplicity, what the fundamental theorem of algebra tells us is that you have a full flight of n roots, okay? Okay, so this is very useful, but there's one more fact that I want to say. So the fundamental theorem of algebra. Fundamental theorem of algebra over the real numbers. So this concerns what happens when your polynomial has real coefficients. Maybe I'll do this in blue. If a polynomial with real coefficients has degree n greater than or equal to 1, then it can be factored into degree 1 and degree 2 irreducibles. Degree 1 and irreducible quadratic factors. So what in the world am I talking about? Remember that by the roots factor correspondence, every degree 1 factor in the factorization corresponds to a root of the of your polynomial counted with multiplicity, right? But sometimes you're going to run into what are called irreducible quadratic factors, and these are going to be things like ax squared plus bx plus c, where the discriminant b squared minus 4ac is negative. If the discriminant is negative, then you know when you try to use the quadratic formula to find the roots of such a polynomial, you're going to fail over the real numbers, right? I should say, these degree 1s, these are themselves having real coefficients. Yeah, it's a little complicated. But the point that I'm trying to make is that there's no such thing as an irreducible degree 3 polynomial over the real numbers, right? You can always factor that into at least one linear factor, and then maybe a degree 2 polynomial, which is irreducible. Sometimes that degree 2 polynomial is reducible, in which case you can further factor it into more linear factors. But I'm running up against time, so maybe what I'll just do is end this video here and maybe explain this idea as it comes up in the future, which I believe that it will. Okay, so we'll leave that be for now, and yeah, call it a day. Okay, so long.